Hello. In this video, as promised, this follows on scientific notation and using it in calculations. So the first one I'm going to do is, I think, fairly straightforward. I was talking to a friend, and he works for IBM, and he was talking about certain calculations that IBM computers are doing, and they're talking about teraflops per second, or I think it's teraflops, but a flop is the number of calculations per second that something can do. So imagine that a computer could process, let's say, 153 megabytes of information in 37 microseconds. So here again, notice how compact the expression is. I could say it is dealing with 153,000,000 bytes of information in 0.0000037 seconds, which is almost unintelligible. 153 megabytes in 37 microseconds is something that we can write down, particularly when we get comfortable with these prefixes, which I encourage you to do prior to starting the semester. Now, if I wanted to know the rate at which it is processing information, whenever we talk about a rate, just like when we talk about our rate of travel on the highway, we say 37 miles per hour. It is whatever is of interest over time. So again, we can make analogies to things that we're familiar with. So here we might say 153 megabytes over 37 microseconds. But now to actually do a calculation and figure out how many bytes per second, I'm going to encourage us to make that mental substitution and plug in the times 10 to the 6th for the capital M. So again, notice we're like surgically removing it, sticking in times 10 to the 6th in its place, and then we'd still have bytes. We're going to do the same thing here. Micro is 10 to the minus 6. And we'd get 37 times 10 to the minus 6 seconds. The micro drops and the seconds remains. Now you could take out a calculator and do 153 times 10 to the 6th divided by 37 times 10 to the minus 6. Notice we might be tempted to say, oh, these kind of look the same, close enough, positive 6, negative 6, what's the difference? I'm just going to cancel these and cross my fingers and hope that they cancel. If you find yourself feeling a little uncertain, just go ahead and calculate it. And in fact, these do not cancel. The only way it would cancel if it was 10 to the 6th in the numerator and 10 to the positive 6 in the denominator too. It's not 10 to the positive 6, it's 10 to the negative 6, so we can't cancel that. If you calculate this using your calculator, you would in fact find this to be 4.13 times 10 to the 12th. And now in terms of units, we'd have bytes remaining in the numerator and we'd still have seconds in the denominator. And I would encourage you to write it this way initially. And then you could rewrite this as 4.13 times 10 to the 12th bytes per second. Or we could say 4.13 times 10 to the 12th bytes. If you want to write it all on one line, now we can use the slash. But I think for calculation purposes, it helps to be explicit with the straight line and put the seconds directly under it rather than writing it like this. Because if we were to try to do some further conversion with seconds, it gets very confusing. So I really strongly encourage you to use this formulation. One last thing you might see then in textbooks would be 4.13 times 10 to the 12th bytes, seconds to the minus 1. Do you see one more substitution we can make? Going back to the very start of the last video about scientific notation. What was times 10 to the positive 12? That's right, it was tera. So we could say 4.13 terabytes of information were being processed per second, or for every second. So this would amount to 41300000000 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I guess we need one more zero there. Bytes per second would be another way to write it, but who likes this? Nobody likes that, right? We like that or that. Okay. So here's just a little challenge for you. Express 0.000000279 grams using first, a decimal and a prefix or a number and a prefix. Go ahead and see what you can do. There's actually two acceptable ways to use scientific notation prefixes here, or I should say common. So go ahead and pause the video, and again, I really strongly encourage you to take out a piece of paper and commit. Okay, we count 1, 2, 3, 4, 5, 6, so we could put the decimal there, and 0.279 grams. Notice I'm in the habit of writing that zero prior to the decimal. That's another thing I would encourage you to do. As you begin practicing problems, write that zero, because I see a lot of students doing this, and if you write it very faintly, a lot of students forgetting that they wrote it. And then they think it's 279, and then do a calculation, and they're off by a factor of 1,000. Right? You might say, oh, well, just a small mistake, not a big deal. But if somebody gave you 27 cents versus $279, you'd be upset, right? So it's not a small mistake. If you're talking about building a bridge and you're off by a factor of 1,000, not a small mistake. Okay. So doing things that help you get problems right is the key to success in general chemistry, and that's practicing problems and trying lots of different things for yourself. So again, that initial zero is helpful just to make sure that you emphasize that there is in fact a decimal. Okay. So if we wrote it this way, 0.027, I shouldn't have written the grams there, we swung it 6 decimal places, so it would be 0.0279 times 10 to the minus 6 grams, and then we can make the substitution 0.279 micrograms. So this would be one of the acceptable ways to write it. Or if we came along and did 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places, we could say this is 279 times 10 to the minus 9 grams. And you remember what minus 9 is because of the alliteration. Right, it's nano, so this would be 279 nanograms. Right, so this, and this are 5 different ways of expressing the same quantity, the same mass. My personal favorite would be that. I think it's the clearest, it's the most succinct. I understand 279. I think in terms of whole numbers. I have a harder time thinking in terms of decimals. I don't know what 279th of a gram is. I mean, honestly, I don't know what a nanogram is. It's not a quantity we can weigh out. It's not a quantity that we deal with in lab, but we can do calculations about nanograms. Okay. But 279 of them, I get that. So I think that's easiest. This is clearly the least useful in terms of communication. So we try to substitute out for something like that. Okay, here's another problem. 3.8 milligrams over 5.9 microliters. This is a gram over volume. This is a density that you're calculating. The first chapter deals with density, so hopefully you've read through that and done some density calculations, but grams over volume. Go ahead and calculate this in units of grams per liter. And again, I recommend pausing the video. All right, if we do this, we would take 3.8. I make that mental substitution, or in this case, the physical substitution, 3.8 times 10 to the minus 3 grams, 5.9 times 10 to the minus 6. Drop the micro, add the liters. So I'm just plugging that in. This keeps me from getting things wrong. And notice I'm not even doing 3.8 milligrams, 5.9 microliters, and that there are 1,000 milligrams in a gram, and that there are 10 to the 6th microliters in a liter. That would be one way to get at the same answer. I guarantee that you'll get it right. Milligrams would cancel milligrams, microliters would cancel microliters, grams and liters would cancel. I see a lot of students getting these kinds of things wrong. Notice even here, I've now switched to saying that there are 1,000 milligrams in a gram. I'm used to that conversion. You could also write this as 10 to the minus 3 grams in a gram. Same thing. Notice if we had 1 over 1,000 is equal to 10 to the 1 over 10 to the third. 1 over 10 to the third is 10 to the minus third. So that should be a milligram down there, right? So I see a lot of students get confused by, oh, do I write it this way? Do I write it that way? If you know how to do that and get it right every time, perfect. Do it. However you've learned it, keep doing it if you're getting things right. If you're not getting things right, or if you think this seems confusing, I would use my little trick, which is, hey, milli is 10 to the minus 3. I'm going to take out milli. I'm going to substitute in times 10 to the minus 3 for that little m. I don't have to think about it. Grams. Micro, 10 to the minus 6. Going to take that micro out. Going to put in 10 to the minus 6. My liters are still there. All I've taken out is that micro symbol and replaced it with its numeric value. And now if I take 3.8 times 10 to the minus 3, divide by 5.9 times 10 to the minus 6 on my calculator, I got 644. And the units here are still grams over liters, or 644 grams per liter, or 644 grams liters to the minus 1. Okay. All equivalent ways of expressing the same thing. So a lot of this is finding ways that you're comfortable with, that you get things right all the time, and thinking about the magnitudes of these things. Now, here's a bit of a challenge problem. E is equal to hc over lambda. We've seen this now a couple times. And here's a question. What is the wavelength? So we're looking for lambda of light. And I want it expressed in nanometers of light that has energy of E equal to 8.37 times 10 to the minus 19 joules. So this is going to wrap up a lot of stuff that we saw in previous videos and now add in the expression of these things using scientific prefixes. So we recall that H is equal to 6.626 times 10 to the negative 34 joules times seconds. The speed of light is 2.998 times 10 to the 8 meters per second. Some people know this as 2.998 times 10 to the 10th centimeters per second, but notice the unit change, that times 10 to the 10th centimeters. Yeah, it goes more centimeters than it does meters in a second because centimeters are smaller, 100 times smaller. So instead of 10 to the 8th, it goes 10 to the 10th, or a factor of 100 more centimeters per second. Okay. So go ahead, pause the video and work this problem, solving for the wavelength of light. If you haven't paused it and you're still hoping you're going to see the answer, I, again, would really encourage you to go ahead and pause, try it. You'll learn a lot more. And that's what this is really all about. Risk-free, you get it wrong, no big deal. I'm going to, we'll work through it together. So, okay, so we're back. We want to solve for the wavelength. We could go ahead and plug in numbers and work with the numbers. But if we really want to be efficient at this, again, we'd recognize that we're going to need to cross multiply, or multiply this side by lambda, multiply that side by lambda. We get lambda times E is equal to HC. The lambda would cancel. And then we'd want to get rid of E, so we'd have to divide both sides by E. So we'd get lambda is equal to HC over E. Now, I see a lot of students doing this on exams and in class. That's fine, but I would encourage you to work past this and convince yourself that every time you do that, that whatever was down here comes up on the other side of the equal sign, and whatever was in the numerator here goes down into the denominator on that side, and just be content, or convince yourself of that. Don't be content, don't take my word for it. Convince yourself that that's the way it works. So that you can very quickly, anytime now that you see E is equal to HC over lambda and you want to solve explicitly for lambda, you could just say lambda, bring that over in your head, HC, that comes down like that. If I wanted to solve for C, right, we'd want to keep C up there. We would need to multiply by lambda. We would need to divide both sides by H. So we should be able to write that very quickly now. So it's a more mature way of working with equations. So push yourself to adopt things that will help you solve problems quickly. It will be of great benefit on exams where you are expected to know or be able to do this pretty quickly. I write exams where I expect students not to have to take time to do that, but rather do it relatively quickly. So if you're at this stage, fine, work out of it, grow. That's what I'm encouraging through these videos. All right, one last thing, we'll solve this problem now. Lambda here is equal to H. We're going to plug in. Including units. Don't drop the units. If you didn't write in units, go back, shut the video off, write in the units, because the units are just as important as the numbers. And then the energy was given as 8.37 times 10 to the minus 19 joules. Now I'm going to look at units first. We've got joules in the numerator, joules in the denominator. Joules cancel. I'm going to cross that out. Seconds in the numerator of the numerator cancels reciprocal seconds that are also in the numerator. So the last unit standing is just meters, and the meters is in the numerator of the numerator. So I know whatever number I generate on my calculator is going to be in meters, not the nanometers that I was asked for. So little flare should be going off in your mind saying, okay, I'm going to have to do something at the end of this problem to convert into nanometers like I've been asked for. Again, this is communication. There was a NASA probe to Mars that crashed because the US scientists didn't communicate with the European scientists correctly about the units that they were using. And because of that, the US was using, I think, inches in the or meters or something, and the European scientists thought that they were being given information in meters, and because of that, they incorrectly calculated trajectories, and the thing crashed into the surface of Mars. Imagine if you're somebody who worked for like 6 or 8 years designing one of the instruments that went on that probe, and you found out that it crashed and burned, and you never got any data from the thing that you designed because somebody didn't use units correctly. Would you say that that's a small mistake, or, oh, I knew better? No, I mean, hopefully you'd be forgiving, but that it doesn't cut it anymore to just minimize those kinds of mistakes. So we want to get things right. Now, if you take numbers 6.626 times 10 to the negative 34, multiplied by 2.998 times 10 to the 8th, divide by 8.37 times 10 to the, that should be minus 19 down there. I get on my calculator 0.000000237, right? Because my calculator was not set to show me stuff in scientific notation. So if I'm writing this down quickly on an exam, I'm very likely to make a mistake. The person grading it is very likely to make a mistake looking at the zeros. If you were working in scientific notation, you might have seen 2.37 times 10 to the minus 7. Now we know that these both would carry the units of meters. Here again, we don't recognize times 10 to the minus 7 as something that has an acceptable prefix. So we'd have to go back to thinking about what that means. We have, again, two options. If we go back to this, we could think, well, if we swung the decimal place over that way, we would now have 237 times 10 to the minus 6. Which would be, it would be 0.237 times 10 to the minus 6. And then we could say that would be 0.237 micrometers, also pronounced micrometers. More common here, though, would be to try to not do this in decimals. You saw how difficult it was for me to think about the decimal here. We swing it the other direction, and we get 237, but because we'd be going further to the right, we'd have 237 times 10 to the minus 9, which is 237 nanometers. So again, we're dropping the times 10 to the minus 9 and plugging in the nano. Okay. So in fact, the wavelength of light that has that energy would be 237 nanometers. A nano, 10 to the minus 9. This is a billionth. Take a meter, 3 feet, right? Or yeah, 3 feet long. That's only not even a foot. Imagine 3 of those, but divide that into a billion parts in your mind. I dare you. I challenge you. It's really hard to think about billions. But if we had 237 of them and a wave, when we talk about wavelength, light propagates as a wave. That wave would be 237 of those tiny, tiny, tiny little pieces. Each peak of the wave that light travels would be 237 billionths of a meter apart from each other. It's really, 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 really small. And in fact, this wavelength of light turns out to be in the ultraviolet region of the spectrum. So we wouldn't see it with our eyes because our eyes is insensitive to wavelengths of light that small. Have to be a little bit bigger. Have to get over about 400 nanometers. We do perceive things that are 400 nanometers. That's blue light. So that wraps this up, but this shows how we're going to use scientific notation in calculations. Again, we could even get an estimate. I should point this out. We have 10 to the minus 34 times 10 to the 8th over 10 to the minus 19th. 10 to the minus 34 times 10 to the 8th. We would add those two things together. Well, negative 34 plus 8 would be 10. Please let me do this right. 10 to the minus 26. Now we would divide by 10 to the minus 19. When we pull that up, it becomes 10 to the negative 26 times 10 to the positive 19. And we'd get something on the order of 10 to the minus 7. Which is, in fact, about what we got. We get a fraction here. 6 times 3 would be about 18 divided by 8, so about 2. So I don't know if I've done something wrong here. Negative 26 plus minus 19. Something's not computing, but we can estimate where we are, just not seeing it. Maybe this isn't right. Maybe that should be 10 to the minus 8. Anyway, we can get a sense of the magnitude that we should be getting just by looking at the magnitude of the exponents on the 10. Okay. So hope this helps. Next video will be on a different topic, but if this helps review exponents and why we use them, again, why do we use them? Communication. No other reason. It's simpler communication, clearer communication. And I hope you have a good rest of your day. Bye.